Section 4.6, Properties of Natural Log Functions. So, we have this thing called the natural log. It is the inverse of the exponential function. And so remember that our definition, y being equal to the natural log of x, is exactly the same thing as x is equal to e raised to the y. And so another way to think about logarithms is that a logarithm is actually a power. And so a logarithm is a power. And so our properties of natural logs and logarithms of general are specifically going to come from our exponent rules. And so if you can think about the fact that logarithms are powers, then hopefully you can recognize what's going on here. So the natural log of a product, that is, the natural log of x times y, is the same thing as the natural log of x plus the natural log of y. Then, if I want to take the natural log of 1 divided by x, that's actually going to be the natural log of an inverse, and this is an interesting property. This is actually going to be the same thing as negative natural log of x. Then we have the natural log of a quotient. That is, if you have the natural log of some x divided by y, that's going to be the same thing as the natural log of x minus the natural log of y. And then if you have a natural log of a power, so if I have specifically the natural log of x raised to the b, that's the same thing as b times the natural log of x. And so if you have powers inside of a natural logarithm on a single item, the power can come out and be multiplied times the natural log of x. Alright, so now I want to revisit some examples that we did in the last part, and that is I had e to the natural log of x plus natural log of 2. Earlier we just used the properties of exponents to solve this. But now what I want to do is I want to use the properties of logarithms to solve this, and then use the inverse properties of e and natural log. And so if I have the natural log of x plus the natural log of 2, recognize that that's really the natural log of the natural log of a product, but in reverse. And so if we have e to the natural log of x plus natural log of 2, that's the same thing as e to the natural log of 2 times x, right? X times 2, and so that's the natural log of 2x. Now I'm just using the natural log of a product from right to left. Well, then recall that e raised to the natural log of anything is that anything, and so that's going to be 2 times x. Caveat, anything has to be within the domains and ranges properly, but we're assuming that this is fine. Alright, so then I have e to the 6 times the natural log of x squared. Well, this is 6 on the outside, and so this is the backwards part of natural log of a power. So I can take this 6 on the outside of natural log and put it as a power on the inside. So this is the same thing as e raised to the natural log of x squared raised to the 6th power. Well, that's then going to give me e to the natural log of power to a power as a product, and so that's x to the 12th inside a natural log, and then e raised to all of that, and then e raised to the natural log of stuff is the stuff, and so we're just left with x to the 12th. Now let's just do some more simplifications using more of the logarithm rules. Now, notice that we have some pluses and minuses of logarithms, which means that sooner or later we'll be able to use either the product or the quotient stuff inside of the logarithms. But before, we have to deal with the coefficients of the logarithms because those become powers on the inside. And so if I have 5 natural log of x, that's the same thing as natural log of x raised to the 5th power. Then, notice that if I have negative 1/2 natural log of y, you have two choices. You could pull in the negative 1/2 and put it as a power on y. That is a choice that you have, or you can leave the negative out front. That's up to you. I think I'm going to leave the negative out front just to see another property. And so this is then going to be minus the natural log of y raised to the 1/2 power. Then I have plus 3 natural log of z, and so the 3 goes on to the inside, and that's going to be plus the natural log of z raised to the power of 3. Then at this point, notice that I have the natural log of x to the fifth minus the natural log of y to the 1/2, which means that we have the natural log of a quotient rule, but backwards. And so that's the same thing as then you can combine this subtraction as a quotient inside the natural log. That's the natural log of x to the fifth divided by y to the 1/2. Then plus the natural log of z cubed. Well, then I have plus, and so that's going to be the product inside of a natural log. So the addition of logarithms is the product of the arguments of the logarithm. That's then going to be the natural log of x to the fifth over y to the 1/2 times z cubed, or x to the fifth z cubed, all divided by y raised to the 1/2 power. And for these, often enough, we're just trying to do some simplification to a single logarithm. That's what we've done, and here we are. Alright, so for number 3 here, we want to know natural log of 9x minus natural log of 3x is equal to what? And so I would recommend that at this point you pause, you try the work, and then you select the correct answer. Assuming that's what you've done, I'm now going to do it myself. So if I have natural log of 9x minus natural log of 3x, I recognize that this is a quotient. And so that's the same thing as the natural log of 9x divided by 3x. Then I just reduce that fraction inside the natural log, and I have the natural log of x divided by x is 1. 9 divided by 3 is 3. And then I get the natural log of 3. And so that is my solution. Alright, so at this point, what I want to do is I want to use what we know about derivatives and what we know about functions with exponentials to be able to rewrite and answer the question as to where this function is increasing, where this function is decreasing, where it has its maximums or minimums, where it's concave up, where it's concave down, does it have any inflection point, and where does the tangent line have a slope of 5. And so specifically what we're about to do is we're about to take derivatives, use the first and second derivative test to answer all of these questions. So, first off, I need to find f prime, because remember that if I can find f prime of x, then the first derivative is actually giving me the answer about slope. And if I can find the zeros of slope, that's the places where we have changes in slope. That is, we go from increasing to decreasing, or from decreasing to increasing, or we just have flat spots in general. And so if I'm trying to figure out where we're increasing, first derivative sounds like a good place to start. Decreasing, same answer. Where we have maxes and mins, well, I'll use the first derivative in the second derivative test. And then concave up is just second derivative, concave down is second derivative, inflection point second derivative, and tangent line is first derivative. Okay, so f prime of x, if I have negative 3x plus e to the x, remember that the derivative of sums is the sum of the derivatives. Therefore, taking the derivative of f of x, I take the derivative of negative 3x, which is negative 3. Then I take the derivative of e to the x, but the derivative of e to the x is e to the x. So I found the first derivative. We're going to use it, but since we're going to have to use the second derivative, let's go ahead and find the second derivative as well. And so f double prime of x, that's going to be the derivative of sums is the sum of the derivatives. And so the derivative of negative 3 is 0, but I'm not going to leave it. And then the derivative of e to the x is e to the x, and so I have found the first and second derivative. Wonderful. At this point, if I want to know where is this function increasing, we can use the first derivative for that. So I need to find where is the first derivative 0, or where can we have a possible maximum minimum. So locations of possible extrema, that's going to occur when the first derivative is 0. So 0 is equal to negative 3 plus e to the x. So we want to solve for x, so how about add 3? Add 3. That then gives me that 3 is equal to e to the x. At this point, I actually want to rewrite this x. I want to solve for x in a way. And so I'm going to use the definition about natural logs. That is, the natural log of 3 is equal to x. That's specifically a possible location where I have a maximum or a minimum. And so I want to go ahead and say that where do we have a maximum or minimum? Well, possibly where x is equal to the natural log of 3. And I'm going to make note of that right now, and I'm going to put a question mark because we do need to check it, and we'll need to figure out where that max or min is, but I'm going to start with that. X equal to the natural log of 3 is where we might have a maximum or minimum. Alright, but then let's use that first derivative, and let's think about this for a moment. If I cut up the number line and I write the natural log of 3 here, that's where I'm going to cut up the number line. Now, if we don't know where the natural log of 3 is, then luckily our calculators have a natural log function, and so the natural log of 3 is going to be approximately 1.1. That's close enough for all intent and purpose, and so I'm going to pick a value to the right of 1.1, and I'm going to pick a value to the left of 1.1. I'm going to plug it back into my first derivative to figure out if I get positive slopes or negative slopes. Because at this point, if I can figure out if we have increasing or decreasing slopes, then I'll know if this is a maximum or a minimum, and I'll also know where this function is increasing and decreasing. So great. So my slopes to the left of 1.1, that's going to be f prime of, well, how about 0? 0 is an easy thing to calculate. Well, if I plug in 0 into my first derivative, that's going to be, I'll write it down here, f prime of 0, that is negative 3 plus e to the 0, but e to the 0 is 1. Negative 3 plus 1 is then going to give me negative 2. So f prime of 0, f prime, the first derivative to the left of 1.1, is negative. And so if that's a negative slope on the left of 1.1, technically that's going to mean that we're decreasing to the left of 1.1. But before I answer my increasing and decreasing question, I need to double check what happens to the right of 1.1. So to the right of 1.1, how about we find f prime of 2? So f prime of 2, well, we're probably going to have to do an approximation here because that's going to be negative 3 plus e raised to the positive second. And I'm going to let my calculator do the work. That gives me 4.4 approximately. And so if that's approximately 4.4, that's going to be a positive slope to the right of 1.1. And specifically now I know that the slope is 0 at the natural log of 3. To the left of natural log of 3, it's a negative slope. So negative slopes are decreasing. Positive slopes are increasing. And so then I can use what I've just found using the first derivative to answer the question. This function is going to be increasing, specifically to the right of the natural log of 3, in terms of interval notation, or if you wanted to write in terms of x, it's increasing when x is strictly greater than the natural log of 3, or if you wanted to write that in terms of interval notation, that would be from the natural log of 3 up to infinity. Whereas if we're concerned about decreasing, well, it's a negative slope to the left of natural log of 3, and so that's going to be where x is less than natural log of 3, or in interval notation, that's going to be from negative infinity up to the natural log of 3. And so now I have increasing and decreasing intervals, or inequalities. But now that I've figured out where it's increasing and decreasing using the first derivative, I claim that we have the answer to a maximum or a minimum. Specifically, we have a positive slope to the right of natural log of 3. We have a negative slope to the left of natural log of 3, which means that I know now that I do have extrema because we have a change from negative to positive. But if you were to think about what happens if you were changing the slope from negative to positive, well, that means that you have a minimum. And so I know specifically that I have a minimum at x equals natural log of 3. Well then, if you really wanted to know what was the ordered pair, or what was the minimum, well, that's going to be the ordered pair, natural log of 3. Plug that back into my function, f of natural log of 3. That's going to be equal to negative 3 natural log of 3 plus e to the natural log of 3. But remember that the natural log of 3 as a power on e gives us 3. And so this is then negative 3 natural log of 3 plus 3. And so I'm just going to write that as my minimum. So now we know that our minimum is specifically negative 3, natural log of 3, plus 3. You could use a power rule on natural log if you so desired. Alright, well then let's answer the question about concave up versus concave down. When and where? So, all we need to do is look at our second derivative. So second derivative, f double prime of x is equal to e to the x. Well, let's think about this a moment. Is e to the x going to be positive or negative? Well, I claim that if you recall the properties of e to the x, as long as it's a positive power, is all positive. No matter what you plug in for x, I don't care if it's negative 5 million, it's going to be a positive number. And so since the second derivative is bigger than 0 or positive, I know that this function is concave up everywhere on the domain, or specifically concave up from negative infinity to positive infinity, or that is everywhere. And so it's concave up everywhere, that is from negative infinity to positive infinity. And so if that's the example, then where is this thing concave down? And specifically, it's concave down nowhere. Then we have to ask ourselves, where are the inflection points? Well, once again, because I found the second derivative, the way you would find possible inflection points is you would set the second derivative equal to e to the x. But if you set e to the x equal to 0, that thing has no solutions. And so, are there any inflection points? The answer to this question is no. No inflection points. Well, then we want to know, where does the tangent line have a slope of 5? So specifically, what are we going to do? We're going to set our first derivative, f prime of x, equal to 5. But if it's equal to 5, that means 5 is equal to negative 3 plus e to the x. And so if I want to know where this thing has a line with a slope of 5, solve this equation. I'm going to add 3. Add 3, I get that 8 is equal to e to the x. If I want to solve for x, I'm going to rewrite this using my natural logarithm definition. And so using the natural log definition, this is then going to be x is equal to the natural log of 8. And so I know that the tangent line when x is equal to ln of 8 is specifically where we have a tangent line with a slope of 5. But let's, of course, find the ordered pair, so let's plug that x back into our original function f. And so f of natural log of 8 is equal to negative 3 times the natural log of 8 plus e raised to the natural log of 8. And so e raised to the natural log of 8, well, that's just going to give me 8, and so I get negative 3 natural log of 8 plus 8 is my y value where the tangent line has a slope of 5. So the tangent line has a slope of 5 at the specific ordered pair, natural log of 8, negative 3 natural log of 8 plus 8. And so that's the ordered pair.